So 2.6. All right, so let's start. We talked a few days ago about, we had our rational root theorem, and we talked about what a rational number was. So now we're going to talk about rational numbers. So rational functions. So let's decide what we might be talking about when we're talking about a rational function. So what do we think? What would rational mean?
Real.
We're talking about real. Our coefficients. Our coefficients are real. Yes. So that plays a part. What did we decide that the root of rational was? Ratio. And a ratio is a fraction. So this has to do with fractions. So a rational function is a function that is a fraction wrote the first couple words and then the last word, or the letter. A fraction of polynomials. And we have grown to love polynomials over the course of the chapter, and now we're doing something slightly different with polynomials. So we're going to write our rational function. I'm going to say f of x equals n of x for numerator over d of x, denominator. And n and d are are polynomials. So the things that we've been learning about polynomials come into play when we talk about rational functions. We know how to find zeros of polynomials. Well, that's an important thing to do for rational functions as well. Because when our numerator is 0, when our denominator is 0, it's going to tell us things about this function. In general, finding zeros of functions is an important tool moving forward. You'll be finding when functions equal 0 a lot. All right. So we have this rational function. When we have a function like this and we're looking at the domain, what do we have to be careful about? The denominator can't equal 0. So our domain is where our denominator does not equal 0. And just to kind of give it a reminder about how the different ways that you might be asked this question. If the question asks you for the domain, it's asking you what is allowed. So if I looked at something like f of x equals 2x plus 1 over x squared minus 4. So what would be the domain of this rational function? So that's where we want to be careful. The domain is where the denominator is not equal to 0. So we're going to say x cannot equal plus or minus 2. So if we wanted to state the domain, we would say real numbers, all real numbers, except for x equals plus or minus 2. So the domain is not the part that we're leaving out, the domain is the part that we're keeping. So we could say all real numbers, we could say something like negative infinity to negative 2. Our book likes to do it this way. Union. I'm not going to write it out because it'll be more confusing. Anyway, we could say negative to negative infinity less than x less than negative 2, etc. So we could write it out that way. The easiest way is to say all real numbers except x equals plus or minus 2. So the domain's what's allowed. All right. What would make this function equal to 0? What is it? The numerator equals 0. F of x equals 0 when the numerator equals 0. When our function equals 0, what does that tell us about our function? X-intercepts. So this gives us our x-intercepts. So if the problem asks you find the x-intercepts of the graph of this function, it's asking you where is the numerator equal to 0. That's going to be our x-intercept. What is another word for that, what we're looking for there? Solution to f of x equals 0. What's another way of saying that? It's a 0 of the function, yes. And one more way? Root, a root of the function. And it would be a factor of the numerator, but it wouldn't necessarily be a factor of the entire function. So root intercept 0, solution when the numerator equals 0. Interesting things happen when we graph these rational functions. Everybody good with this? Okay. Does anybody remember what the graph of y equals 1 over x looks like? I see some kind of hand motions there. Yeah.
Like forms asymptote with the is it like a tangent?
So all right. So Jack's kind of consolidated our hand motion. He's doing this.
That looks right.
And that's what Tommy was getting at as well. We have something like this. And we also have it over here on this side. And the x and the y axis for this y equals 1 over x are called, what were they, Tommy? The asymptotes. So we end up with asymptotes. And that's also the title of our section here. So we get asymptotes. We get asymptotes with rational functions. Let me grab another one. I have a picture of another rational function that I want to talk about and shrink that a little bit. I'm just going to grab a picture of that. So I'm going to come back and refer to this one a couple of times. All right, so here's another rational function. Polynomial in the top, 2x minus 5. Polynomial in the denominator, x minus 2. And so if I draw this a dotted line here, and I didn't make my drawing really, let me erase that and make it a little better. That looks a little better. And then I also have this horizontal line here, like so. So we get a vertical asymptote at x equals 2. Anybody see anything special about x equals 2 for this rational function? It makes the denominator 0. And then this horizontal line is at y equals 2, and we'll talk about how that happens in just a second. So we end up with asymptotes. Rational functions can have multiple vertical asymptotes. So we could end up with our rational functions do all kinds of crazy things. So it can look like this. It could go the other way around. So our rational function could look like this. Our rational functions can do this kind of thing. They can do that kind of thing. And if we have more than one vertical asymptote, they can look like our cosecant and secant graphs in between the asymptotes. And then we could get something outside here like this. It could look like, our rational function could look like a tangent function or a cotangent function in between the asymptotes. We also get rational functions that do this kind of thing. So all kinds of interesting graphs happen with rational functions. And we'll talk about how we figure out what they look like a little bit today and a little more tomorrow. The rational functions, we end up with asymptotes. They do. Graphs are really interesting looking. All right, so let's be a little more formal about what we mean by an asymptote. Be a little more mathematically precise. So let's talk about vertical asymptotes first. And from here on out, I'm just going to abbreviate vertical asymptotes by VA instead of writing it all out. A vertical asymptote is a line. So a vertical line is x equals a constant. So the line x equals a. So some constant, x equals a, is a vertical asymptote if f of x, the arrow we pronounce approaches, plus or minus infinity as x approaches a. Sounds complicated, but all this is saying is, let's go back to this picture. As x gets close to 2, my function approaches negative infinity. On this side, as x gets close to 2, my function gets really, really big and approaches positive infinity. That's what we mean by an asymptote, a vertical asymptote. So x is getting really, really large, shoots way up or shoots way down. And it's important to remember that vertical asymptotes are lines. So the vertical asymptote isn't 2, it's the line x equals 2. Horizontal asymptotes. And I'm going to abbreviate horizontal asymptote by HA. On your test, if I write HA, I'm not laughing. I'm saying horizontal asymptote.
Joke's on you.
Last year I had. Why did you write ha on my test? That's kind of mean. And we all know that I'm not mean by what I say, just by the problems I solve. The line y equals b. So horizontal line, y equals a constant. The line y equals b is a horizontal asymptote if our function f of x approaches b as x approaches positive or negative infinity. The horizontal asymptotes tell us what happens eventually. As x gets really big, as x gets really small. So let's go back to our picture here. As x gets really big here, our function eventually gets really, really, really close to y equals 2. As x gets really small, way over here, the function eventually gets really close to y equals 2. And if we have a horizontal asymptote, our function can do all kinds of things. Here's my horizontal asymptote. My function can do all kinds of things here. All we're interested in is, does it eventually get close to that asymptote? It can go do all different kinds of things in between. Does it eventually get close to that asymptote? Functions can cross horizontal asymptotes, yes.
Is that because there's like a bowl?
Holes are separate things. But functions can cross the horizontal. All the horizontal asymptote tells us is what happens eventually. As x gets really big, as it go way out over here, does the function end up getting close to some number? So, like a quadratic function doesn't have a horizontal asymptote because eventually it just gets bigger and bigger and bigger and bigger on either side. So no horizontal asymptote because eventually it gets really big. But a horizontal asymptote means eventually it gets really close to some number. Now we can't cross a vertical asymptote because our function's undefined at a vertical asymptote. So we're always, at a vertical asymptote, we're always going to have a break in the function because it's undefined. It gets close to infinity. So when we like to ask questions about horizontal asymptotes in ways that aren't saying what is the horizontal asymptote of this function. So you might have some function that describes a population. What is the population going to be after 10,000 years? So eventually, is it getting close to something? That's the kind of question it might ask. As x gets very large, is this function approaching some value? So x is getting really large, that's asking you about a horizontal asymptote. All right, questions? All right, let's talk about how we find these things with rational functions. Our rules. And I'll say rules for asymptotes. And we already know one of them. Vertical asymptotes are really easy. So for all of these rules, we're saying our f of x equals n of x, some rational function, d of x, numerator, denominator, that's what the n and d stand for. So our first rule. We have a vertical asymptote when the denominator equals 0. And remember, our vertical asymptote is a line. So we would say if d of some value a equals 0, if the denominator equals 0, when I plug some number in there, then x equals a is a vertical asymptote. The line x equals a. So I just figure out what number makes the denominator 0, and I say x equals that number is my vertical asymptote. So those are easy. So this is where finding zeros of polynomials comes in handy with rational functions. I need to find where the denominator equals 0. All right, our horizontal asymptotes. We have 3 cases for our horizontal asymptotes. And they have to do with the degree of the numerator and denominator, the highest power on the exponent. Our first rule is if the degrees are, which one do I want to do first? If the degree of the numerator is less than the degree of the denominator. So the denominator's degree is bigger. Then our horizontal asymptote is y equals 0. That's telling us the degree of the denominator is bigger. Sure, this should say degree of the x. So we're just looking at the highest power on the variable. So if the denominator is bigger, y equals 0 is a horizontal asymptote. If our degrees are the same, and this sounds more complicated, what I'm going to write next sounds more complicated than it is, then y equals the ratio of leading coefficients is a horizontal asymptote. And we'll take a look at what we mean by that. It's really easy to figure out. Let's say we have f of x equals 3x to the third minus 2x squared plus 5 over 8x to the third minus 2x squared plus x minus 9. The degree of the numerator and the degree of the denominator are the same. Highest power on the exponent. So we're looking at the leading coefficients. We're just looking at the numbers in front of those two highest powers. So this would tell me that y equals 3/8. The line y equals 3/8 is a horizontal asymptote. So that's really easy to figure out. And then finally, if the degree of the numerator is larger than the degree of the denominator, we have no horizontal asymptote. So if the degree of the numerator is bigger, we have no horizontal asymptote. Tomorrow we'll talk about what does happen if that's in that case, in certain instances of that case. So those are our rules for finding our asymptotes. And Jack mentioned another important thing that doesn't really have to do with asymptotes. But what else can we end up with these functions? What was the thing? You talked about a hole? Holes. Yeah, we could get a hole in our function. And our rule for holes are, and I guess it's not an asymptote rule, but we do need to be aware of it. If the numerator and denominator equals 0 at the same time, so we would say d of a equals 0 and n of a equals 0. We have a hole at x equals a. All right, questions about our rules for finding our asymptotes? All right, so all I want to do next was go over a couple of examples of looking at these and how we work with these rational functions. Decide about holes and asymptotes and all that kind of thing. And tomorrow we're going to sketch graphs of rational functions. I'll talk about what the graphs look like today, and tomorrow we'll work with actually sketching the graphs on our own. So let's look at a couple of examples. So f of x equals x plus 1 over x squared minus 1. We want to find horizontal asymptotes and vertical asymptotes. So the easy one to find first is the horizontal asymptote. So the degree of the numerator and the degree of the denominator, how do they compare? The denominator is bigger. So what does that tell us? Y equals 0 is our horizontal asymptote. If the denominator is bigger, then our horizontal asymptote is y equals 0. And if our function, so we can find our horizontal asymptote easily just by looking at the powers of the numerator and denominator. If our rational function isn't factored, we should factor it in the numerator and denominator. So I get x plus 1. How do I factor x squared minus 1? X plus 1, x minus 1. So our vertical asymptote is when the denominator equals 0. So what makes our denominator equal 0? X equals plus 1, right? What happens at x equals minus 1? They're both 0 at the same time. The numerator and denominator are 0 at the same time. So we have a hole at x equals negative 1. And if we sketched a graph, the graph of this function would look something like this. So we have a horizontal asymptote at y equals 0. So there's my horizontal asymptote. We have a vertical asymptote at x equals 1. And in order to figure out where the graph goes for our asymptotes, we would have to plug in some numbers and calculate. If we plugged in some numbers, this would go here. This would go here. And then we have a hole at x equals negative 1. So right there at x equals negative 1, we would have a little place where the graph just doesn't exist at all. Questions there? I think on the homework today, it just asks you to find the vertical and horizontal asymptotes. It doesn't. So we're not doing sketching today. Tomorrow we'll work on sketching. Yeah. If we have a hole, because the numerator and denominator are both 0 at the same time, if we have a hole, there's not a vertical asymptote. It's either a hole or a vertical asymptote. It's not both. So if we have a hole, the graph just doesn't exist. It disappears for a second there. All right. Let's look at another one. And we want to find the horizontal asymptote and horizontal asymptotes and vertical asymptotes. I always like to find the horizontal asymptotes first, just because I think it's often easier. So where's our horizontal asymptote here? 1/2. The degree of the numerator and denominator are the same. So we look at the ratio of the leading coefficients. So we say, remember our asymptotes are lines, y equals 2 over 4, which is 1/2. So we'd have a horizontal asymptote at 1/2. Vertical asymptote, 3/2. How do we find our vertical asymptote? Set the denominator equal to 0. So 4x minus 6 equals 0. Solve for x. So I would get x equals 6/4 or 3/2. And if I sketched a graph, just so we have an idea of what this looks like. This looks like the one we had earlier. There's my horizontal asymptote at y equals 1/2. There's my vertical asymptote at y equals 3/2. To figure out how the graph went between here, because it could go all different kinds of places here, you'd have to plug in some numbers and calculate. So this graph would look like that. How about this one? Let's look at the horizontal asymptote first. How the degree of the numerators and denominators compare. Numerator is bigger. What does that tell us? No horizontal asymptote. So I could say none. How about a vertical asymptote? X equals -1. Remember, it's a line. We need the equation of a line. This one turns out, and we'll talk more about this tomorrow, because the degree of the numerator is 1 more than the degree of the denominator, we have what we call a slant asymptote. And if we were to graph this, and we'll talk about how we find that tomorrow, we have a vertical asymptote here at -1. And what our asymptote turns out to be, the other one rather than horizontal, it turns out to be slanted. So we end up with something like this, some slanted line, and the graph for this rational function ends up going between the lines like so. And we'll talk about how we find the equation of that line next time. We call that a slant asymptote or an oblique asymptote. And we can also have, we don't really get into it, but we can have a quadratic asymptote. We can have a cubic asymptote. We can have a 5th degree asymptote. All right, are we good there? I just have one more question. What if we had something like this? And we wanted to find our vertical and horizontal asymptotes. What would we have to do to find our vertical asymptotes? We have to factor the denominator. So we end up with x plus 5. Does this factor? X plus 2, x plus 5. So if our rational function isn't factored, we usually have to factor it at some point to figure some things out about it. Yes?
Will there be any quadratic?
I don't think so. I think they all factor nicely. But if you couldn't factor it, you would have to use a quadratic formula to find where the asymptotes would be. And what do we see that's special about this one? This one would have a hole at x equals -5. Okay, questions? All right. All right, there you go.